Good evening, everyone. My name's Adam Madgett, and I'm the HyDeploy project manager for Northern Gas Networks. Before we start, I'd just like to say thank you very much for joining us tonight on behalf of Northern Gas Networks and the HyDeploy project team. It's fair to say that we've had a huge amount of interest in this webinar, so we just want to say thank you very much for joining us to hear an update on the project. I just want to get in there straight away that Tommy and I both have young children. So if you hear any screaming babies, that's just a COVID for us, unfortunately, but we'll do our best to get through this tonight for yourselves. So moving on then, you may have heard the recent announcements from government with regards to their 10-point plan for a green industrial revolution. And I think front and centre this is the commitment for hydrogen, and exploring the use of hydrogen for not only heating our homes and businesses, but also exploring further uses across transport and power generation. So the presentation tonight really is more relevant in the current situation, and it really shows that a blended hydrogen future is now a distinct possibility rather than just a pipe dream, excuse the pun there. So the agenda for tonight from myself and Tommy. Tommy, do you want to slip to the next slide? Thank you. So we've got a project overview from Tom Isaac at Progressive Energy. Then I'll be giving an overview of the Winlaton trial, followed back to Tommy for some gas safe messages, and then some Q&A. Now, what we've tried to do with the Q&A is group all of the questions that were sent in as part of the registration into relevant themes, and we tried to answer them within the presentation. There is also a Q&A function you'll see in the bottom right of your screen, so feel free to submit a question into that, and subject to the relevance and time, and we'll try and get these answered in the webinar tonight as well. So without further ado, I'll hand over to Tommy Isaac from Progressive Energy to give an overview of the HyDeploy project.
Brilliant. Thanks, Adam. So my name is Tommy Isaac. I'm the principal engineer for Progressive Energy. We are the overall project managers of the program. Just to give you a quick introduction to the partners on the program. So we have NGN, who Adam represents on the call, as well as Cadent Gas. These are the two GDN sponsors of the program and the two program leads. We then have ourselves, Progressive Energy, who are the overall project managers of the program, putting together the consortium. We have HSL, who are the lab end of the HSE, who handle all of the technical aspects of the program. Keele University, who are the site host for the first demonstration, and then ITM Power, who are the providers of the electrolyzer to the program. So that covers the admin. So a brief overview of sort of where this project began and why we're spending our time doing it. So as Adam quite rightly pointed out, that there is a real momentum at the moment towards decarbonisation and trying to actually put in meaningful measures to tackle the hard to reach areas. Decarbonisation has taken place primarily through electric vehicle adoption and the reduction of coal power, and there has been a broad acceptance that heat, especially domestic heat, is a particularly hard to reach area, and this is effectively what hydrogen is trying to tackle. Now, why blending, you may ask, given that ultimately we have a goal to achieve, or a target to achieve, net zero by 2050. The reason why blending is important is that it provides that practical first step of hydrogen introduction. So the whole purpose of blending is to try and make sure it is a no change to the gas. So this is primarily associated with the appliances, so no change to current appliances, but also extends towards working practices for engineers as well as the network operators. So why is that important? It's important because the thing that has stopped hydrogen being developed in any meaningful sense up until now is a chicken and egg problem of supply and demand. To go all the way to pure hydrogen, you need the appliances out there to be able to receive it. And you also need the production to be able to produce it. And without either of those being deployed at the same time, the market just doesn't work, because no manufacturer is going to invest in the development of the appliances if there is no production. No production is going to be invested in if there aren't the appliances. So you have the impossible challenge of a chicken and egg, which means that nothing ever actually happens. So what blending does is it breaks that chicken and egg, because what it allows is a supply chain of hydrogen to be built up whilst all of the downstream appliances remain the same. And so once that's been broken, you can then start to incrementally increase the amount of hydrogen in the system, because the supply chain is already established. So that's the primary goal of blending, is to launch the market. In itself, it is a meaningful step towards decarbonisation. So a national rollout of blending would eliminate 6 million tonnes a year of carbon, which is the equivalent of 2.5 million cars off the road. So to achieve that without anyone making any changes is quite a large step, really. So that's why we are doing the project, and this is the project in one slide. So what the project is here to do is to enable the bulk deployment of hydrogen blending across the UK by demonstrating its safe transportation and use. The way we do that is by carrying out 3 demonstrations or trials throughout the programme. Because what that allows us to do is generate evidence that then gets reviewed by the HSE to then be used to support that demonstration under the test of as safe as the current gas. So it is a 6-year programme in total. You can see from the red line where we are now. We are currently operating the first demonstration of hydrogen at Keele University, and we are at the stage of engaging with the HSE to try and agree the safety case to enable the first public trial to be to go ahead next year, which Adam will talk about in a few minutes' time. So the reason why we need a new safety case and why there is lots of research and evidence that's required to enable hydrogen is because we currently have a regulatory limit that prohibits any meaningful hydrogen being blended into the system. So we have the gas safety management regulations, which is the sister regulation to the installation and use, which is obviously more pertinent to the gas safety community. And the gas safety management regulations limit hydrogen to 0.1%. This is purely for regulatory expediency. This is because the regulations were aligned to the North Sea specifications when we switched over from Towns gas to North Sea, and because the North Sea has no hydrogen in it, they just set the limit at 0.1% because it made it easy to administer. Now that limit is quite rightly being challenged, because effectively what this regulation does is it effectively locks in gas towards natural gas. It means you can't really move away from methane because the law just doesn't allow you to do that. So what we are doing is trying to generate the evidence to then challenge that limit to enable hydrogen to be blended into the system. So how do we do that, or what's the regulatory system that allows us to do that? So as part of the regulations, they are governed and managed by the HSE, because they ultimately fall under the Health and Safety at Work Act of 1974. And within the regulations, the HSE is allowed to give exemptions to the regulation, only under the condition that the persons affected by the exemption aren't prejudiced in the consequence of it. And what that means in sort of layman's terms is that we have to demonstrate that the change that we are proposing is as safe as the current gas, i.e. there's no increase in risk from anyone who's going to use that gas, either from a consumer perspective, from an engineer's perspective, and from the network's perspective. So we have to demonstrate that the blend is as safe as natural gas, and then the HSE is comfortable to grant us an exemption to the regulation to enable the demonstrations to take place. And the idea is, if we can broaden that evidence base from small-scale trial all the way to kind of, well, effectively the UK network, then we can effectively have the evidence base to challenge the regulation that says that a whole system change should take place to allow 20%. So how do we do that? We build a safety case. So there are effectively three main technical areas that have to be understood. There is, how does the blend affect the materials of the network and the appliances, as well as the meters, etc. Basically anything that will be exposed to the blend. How does it affect the operation of the appliances? And what are the fundamental gas characteristics of the gas, both for combustion and post-combustion, that kind of govern the system? So all of the procedures that govern safe operation of both appliances, pipework and networks, all fundamentally based on an understanding of the gas's characteristics. So we have to understand what all of the relevant characteristics are to then be able to understand how procedures may be impacted by the change in gas quality. And then all of that evidence comes together into what's called a quantitative risk assessment, which is basically a big logic tree, which allows you to understand ultimately what the overall risk is to consumers based on a change of gas quality. So we can quantitatively demonstrate, prove effectively beyond doubt that there is no increase in risk. And it's only once we've gone through that demonstration that we are able to receive the exemption from the HC. So it is quite an arduous task. It took us 18 months to build the evidence just for the kill trial, and took about 3 months to engage with the HC. It's taken another 18 months on top of that to build more evidence for the trial that we're going to hear about today, and we've been engaging with them for 3 months and have probably got another couple of months left. So you can rest assured that it is an incredibly rigorous process that is required to allow these exemptions to be granted and allow the blending to take place. So this is ultimately what it turns into. This is the hydrogen compound that we've built at Kew University. So you can see on the left, we have a big green box that has an electrolyzer in it, which produces the hydrogen from water. And then on the right, we have a green box that mixes it with the natural gas and maintains a blend rate that then gets supplied to the network. So the purpose of this presentation is to go through the Winlaton trial, so I won't stay too much on the current trial at Kew, but it's just to give you a reference that we've been blending there since October of last year, supplying a blend to 100 homes as well as 30 university buildings. We've had no issues to date with downstream appliances or the network. Effectively, no one's noticed, which is the result that we were looking for. And as part of that trial, what we did was build a boiler house installation with the 4 manufacturers that you see on the screen there, where they lent us a pair of boilers each, and we have run them 24/7, where one from each manufacturer has been run on just normal natural gas, the other one has been run on a blend, and we are giving them an accelerated duty cycles, so either maximum firing, minimum firing, or cycling between the two, 24/7 or over a year. And what that does is put on at least 15 years of life onto those boilers, between 15 and 18 years. And the idea is to basically stress them over the course of a year with a blend to see if there are any long-term impacts that could be seen with the appliances. Now, we are not expecting any impact whatsoever, and how we're trying to demonstrate this is that we have not told the manufacturers which boiler has been installed with which gas, and at the end of the trial, we will then return them to the manufacturers and then ask them to try and tell us which boiler was on which gas. And it is our hypothesis that they will not be able to tell the difference between the two, and therefore we can demonstrate that there are no long-term effects on these appliances. And secondary to that main objective is some flue gas analysis work that we carried out to demonstrate that the current flue gas analyzers used by gas safe engineers are still accurate and appropriate for a blend, and that ultimately turned into some evidence that was then published through Gas Safe with Technical Bulletin 157, which you may have read in May of this year. We will touch upon that slightly more in a few slides' time. That's Kew. If you've got any questions, put them in the Q&A and we'll try and pick them up. But now we're going to move on to the Winlaton demonstration.
Thank you, Tommy. If you could just move over to the next slide, please. Thank you. As Tommy's mentioned, Kiel University is phase 1 of HyDeploy. Phase 2 of the project is the first public demonstration, where we'll be utilising a blend of up to 20% hydrogen in the village of Winlaton near Gateshead, which is up in the northeast. There will be transporting a blend to around 669 homes early next year. This is the next step in the program for HyDeploy, and it's really it's a prerequisite for us to when we're looking further ahead for phase 3 and then ultimately further rollout. As Tommy mentioned, we're mirror imaging the process that we've taken in phase 1, and we're currently in the process of the safety case exemption, which, as Tommy touched upon, is a significantly larger piece of work than what we undertook at Kiel. In terms of, we're looking at a much broader range of appliances and properties and materials, all with the requirement to build up that evidence base for confidence. Looking at a wider network and then beyond into to a further rollout. So, the process has been quite long and onerous, but it's ultimately what we need to do to get to rolling out of the blend across the public area. We hope that we'll get a decision on this in the coming weeks and months, probably likely to be early next year. And on that basis, that allows us then to move forward with the trial. Next slide, please, Tommy. So as I've mentioned in the previous slide, the location is at the village of Winlaton. We've isolated the network from the other parts of the networks nearby by isolation valves. So essentially, the only people that will see a blend will be the customers in that demonstration area. We will, of course, as well have a hydrogen compound. This will be located to the south of the trial area in an existing site, an NGN's network called, existing NGN site called Low Thornley. This is where we will have the hydrogen production equipment and also the hydrogen blending equipment. So essentially, this is based on the same design at Kiel, where the hydrogen will blend with natural gas and then transported to customers. Now, the blending unit itself is designed so that we don't go past that 20% exemption, ensuring that we stay within that limit. Next slide, please, Tommy. I think one thing that's been clear from the project team is that from the outset, we've always identified that we need successful customer engagement for us to move forward for this project. And it's critical as part of the success. We've developed a really rigorous engagement plan, which was built on the learnings that we had from Kiel, where we've had dedicated customer liaisons for the trial area to be able to feed back any questions from customers and any other sources as well. There was a key element to the program was undertaken last November, where we needed to gain access to all of as many properties as we could for the trial. And the reason we needed to do that was to carry out a gas safe check, so that we could identify if there was any unsafe appliances, but also, more importantly, it was for us to build that evidence base of what appliances there are on the network. And what these existing installations look like. And due to the engagement plan that we put together, we was able to get detailed information on 90% of them properties within the trial area. And all of this, as I said, was used to feed into the HSE exemption, really to build that evidence and confidence that we'd gone across that breadth of appliances and understanding what them installations look like. I think from where we are now, it's important to sort of reiterate that this evidence that's been collated has been and that's been submitted to the HSE, is, as Tommy mentioned, is all about proving that it's as safe as operating, or operating a blend is as safe as operating on natural gas. So, a faulty appliance on a blend is no less safe than a faulty appliance on natural gas. And I think that's the key takeaway from that. And Tommy will touch on that in a bit more detail in the coming slide. we're just gonna play a short video which gives a visual overview of the project in Winlaton, and then Tommy, I'll hand back to yourself for the rest of the presentation.
Brilliant, thanks Adam. I'll just get this loaded up. Hopefully all the tech will work.
I'm Linda and I live in the northeast of England in a little village called Winlaton. I had a letter, opened the letter and had a quick look and then looked again and thought, hydrogen? That seems an odd concept. Have I misread that? It just never heard of it, didn't know anything about it, so was quite intrigued to find out a little bit more.
The aim of the HyDeploy project is to demonstrate that a blend of hydrogen up to 20% can be utilised and distributed safely within the gas network. We'll be looking to carry out a public pilot into 670 homes in an area called Winlaton. So all them homes will be heating and cooking on a blend of 20% hydrogen. When you burn hydrogen, there's no carbon emissions. So introducing a blend up to 20% will reduce the customers and the gas network's carbon footprint.
We've got a very challenging target in Gateshead to be carbon neutral by 2030. A trial like this will actually play an important part in that. The great advantage of Gateshead is that it's a very environmentally friendly, very green way of transporting energy.
The real benefit for HyDeploy is that customers don't have to make any changes to their appliances when they're using a blend of hydrogen and natural gas, and we as gas networks don't have to make really many changes as well.
So one of the big things that was reassuring for the customers is that the fact that there'll be no difference at the home, there'll be no difference to how they cook, heat their home, and there'll be no impact outside. So it's very clean and easy for us to turn the hydrogen on and they won't notice a difference at all.
Of course, we've got this great asset of a wide-ranging gas network, and I think it seemed to many people that maybe that was going to be redundant in a green world. Well, with hydrogen, that's not going to be the case.
I've recently become a grandmother for the first time, so I'm very conscious of how my little grandson, who's not quite one yet, is going to grow up and what world he'll have there. So whatever we can do to help reduce the carbon emissions and everything that's happening with the cars and pollution and anything that we can do. And it has actually made me stop and think, what else could I do that may help a little bit?
I've been actually quite surprised at how open customers have been. Yeah, we see it as a bit of a stepping stone to the potential for a 100% hydrogen gas network, so it allows us to build confidence up with public perception, but also our own capabilities to be able to introduce a different gas mix into the networks.
Okay, so hopefully that worked for everyone's tech, and that they were able to view it. We'd be happy to send on a link to the video if anyone wanted to have it for their records or wanted to show it to anyone if they were interested. So what we'll move on to now is really some of the key messages that we're looking to provide to gas safe engineers to try and bring you kind of up to speed with the trial and how it could potentially impact your job. And as you'll find out, the idea is that it shouldn't. So in terms of working protocols, the project itself has resourced a team of gas safe engineers for the entirety of the trial. So this is a team of dedicated engineers to be available 24/7 to respond to any situations that may arise where customers give us notice effectively. Now, clearly, we can't guarantee that they will call us and provide that visibility. So what we've also done is through the checks that were carried out on the appliances that Adam spoke about, where the customer allowed us, we have stuck a sticker onto the boiler or any of the appliance that could have any work done to it, which effectively has a phone number that says, please call this number before you're doing any work, just because it's part of a demonstration and we'd like to understand what's going on. It's not so we can change any work or to impose anything. It's just so we can understand what's going on in the trial area during the demonstration, just so for our own records. So that's the kind of protocols that we're put in place. In terms of the working practices, so what we've been able to demonstrate is that there is no change that's needed for domestic standards to accommodate a blend of 20%. So this goes right across the standard range, including PSI standards as well as HyDeploy standards, across fluid gas analysis, tightness testing, purging, installation, heat calculations, pressure drop calculations, and any other works that you could take place. So there was a very long review which we undertook with BSI and IGEM and some procedural consultants that allowed us to identify all of the procedures that underpin the ACS competencies, and then we just read through every single one of them and basically challenged ourselves to then do any of these criteria, so any of the action levels, any of the working processes or the equipment, is any of it impacted in a way where it would mean that it would be a less safe situation if you just carried on using the same procedure with the blend. And we were able to get comfortable across all of those stakeholders, including the standard owners, so BSI and IGEM, that there was no change that was needed for the domestic setting. So what we are looking to do is to formalise that through a communication by GasSafe to issue a technical bulletin ahead of the demonstration taking place. We've already issued one technical bulletin, so the one I mentioned earlier, 157, which summarises the position on fluid gas analyzers, where effectively we're saying that no change is needed to current fluid gas analyzers, both analyzers that directly measure CO2 and indirectly measure it via an O2 reading. They're both fine. And that was research that was peer-reviewed and endorsed by Worcester Bosch, Baxi, Valent, Ideal Boilers, as well as Kane and Crocon, who manufacture the Anton Sprint range. So we have covered a very broad base of both the appliance manufacturers and the detection manufacturers, one of them mainly doing indirect, one of them mainly doing direct measurement. So we're quite comfortable that all of the analyzers that are used today should work perfectly well with no change. And they are really the kind of key messages. So yeah, we've got a team on standby to provide any support and to have any visibility, and there's no change to standards or working practices required to accommodate the blend. So we'll now go on to a Q&A where, as Adam said, we've tried to summarise all of the questions. So we've got nearly 500 questions, so difficult to cover all of them, but I've grouped them into 6 kind of broad categories, and we've got a slide on each one, which hopefully will answer 80 to 90% of the questions. We'll probably have a bit of time left over from the once that's done. So if there are any questions in the Q&A that look appropriate, then we will pick them up through this before we end. So I'll hand back over to Adam, who will take us through the Q&A.
Thank you, Tommy. I was just trying to keep an eye on the Q&A as Tommy was speaking there. I think I've tried to collect as many questions as possible. Excuse me. That I don't think were captured in this in what we put together here. So by the looks of it, we will have time to go through that. So we'll try and get through as many as possible. And if I haven't captured them all, because there was quite a few rolling through, just feel free just to submit them again, and I'll see if I can capture them the second time round, because it was pretty hard to try and keep track. So Tommy, next slide, please.
Yep.
So there was quite a few questions that came in around, when will hydrogen become normal? And there was quite a few that were in the Q&A just now as well. So I think given the recent announcement from government they've put a timeline and when they anticipate having certain blends and 100% trials online. And we expect by 2025 that we will see large-scale blending across sort of 100,000 homes, and the first 100% hydrogen trials, from around 100 to 100,000 homes. So you will have, some of you may have seen today, there was an announcement from Ofgem where Scotia Gas Networks, so SGN, secured funding for their 100% hydrogen trials up at East Fife, where they're looking to deliver 100% hydrogen to 300 homes. So that's within the next 3 to 4 years, I believe. So you can see, that's where the next steps are. And in terms of looking at by 2030, there is the real there is the real possibility of blending to the whole UK, and also at that time is when we would look to start hydrogen conversion. So as we did from Towns Gas to North Sea Gas, that sectorisation of the UK networks to transcend into that 100% hydrogen future. Tommy, did you have anything to add on that one?
No, you covered it off. So there's a program called HyNet, which, if you're in the Northwest, is relevant to you, where there is a hydrogen program that's being developed there to be able to supply a blend to 500,000 homes in the next 4 to 5 years. So these are projects that are not, and there are multiple other projects around the UK also doing the same thing. So this isn't just a kind of academic report. These are real programs with hundreds of millions of pounds of funding to make them happen. So this is absolutely coming down the line, and it's coming down the line as soon as the projects can be developed.
Thanks, Tommy. So again, another relevant question in the ones that were submitted and also in the Q&As is there any need for retraining and new qualifications? So from a blend perspective, there isn't the need to retrain. We haven't identified that to date. So the natural gas skills that everyone has from now will still transfer across. I think the key thing to sort of get across here is that this is a presentation on downstream of the meter. So beyond the meter. So for gas safe registered engineers, there is currently no change been identified for a 20% blend. When we're looking at 100% hydrogen, that's obviously a completely different gas altogether. So there will be new qualifications required, and the EU Skills is currently working with ACS to define how that hydrogen qualification might look like and how it's sort of rolled out as we look towards a 100% hydrogen future. Next slide, Tommy. So again, there was a few questions on this in the Q&A. So in terms of current appliances, do they operate? How do they operate on a blend, or do they work properly on a blend? So there's been a significant amount of work that the project team has undertaken in phase 1 and phase 2, and we've carried out a lot of testing on tyres, cookers, grills, and boilers. And what we've identified that there is no change in their operation relative to the current range of operations. So this is, the application of the operation is dominated by wobbly limits, as we all know, and with a 20% blend, it remains within the current wobbly limits. Also, in addition to this, what some people might not be aware of, is something that we weren't aware of, and obviously until we started looking at it, is that all appliances since 1984 have all been tested with different hydrogen blends during their production certification. And I think Tommy's got a bit more on that detail that he can share with regards to testing of appliances.
Yeah, so since 1984, all appliances have been tested with 35% hydrogen as part of their certification for sale. And then in 1993, that was updated to 23%. And that's what they require to pass to get their CE marking for sale. So this is actually a large reason why the 20% has been chosen, is because there is a general understanding that all of the appliances out there should be able to operate safely because they've all had testing with higher levels of hydrogen as part of their specification for sale.
Okay, thanks, Tommy. So where we're now. Yeah, so in terms of hydrogen appliances, there's questions of, when will they be ready, and are they any different to current appliances? There's a separate piece of work that the government or BEIS have funded called High for Heat, which is focused on 100% hydrogen downstream in the meter. So they've got a work package which is actually looking at 100% hydrogen appliances, and in specific, boilers, fires, and cookers are all currently being developed and manufactured. I think Worcester Bosch and Baxi have already got 100% hydrogen prototype boilers, and actually they are installed and being tested. They're installed at a facility up in NGN's network in RAF Spade Adam, where we've got a hydrogen house. And the boiler is in there currently working and operating as mine does downstairs and yours does at home. What we do expect is that new legislation will require all new gas appliances to be hydrogen ready by 2025, getting us ready for that 2030 vision of a 100% hydrogen network. And from what we've seen to date, all the hydrogen appliances, especially the boilers, they sort of had the same look, feel, and operate exactly as natural gas appliances. I think that's a key part of the process, is to make sure that this change from a new gas doesn't change the way that we do things at home today. Tommy, have you got anything to add on that?
No, you covered it well. Just to say that on the boiler side, you've got some interesting results coming out of Baxi and Worcester Bosch, who are the two leads. Although there are other manufacturers with sort of more private developments. That obviously, with no carbon in the fuel, there's obviously no CO being produced, as well as no CO2. And what they're also finding is that the NOx levels are also about half of what you'd expect from a natural gas boiler. So from a kind of emissions toxicity perspective and compliance perspective, these are much safer and they are much more compliant with the relevant emissions legislation.
Okay, Tommy, I'll just hand over the last two questions to yourself to talk through.
So we got a lot of questions over how is the hydrogen going to be produced. So for the Winlaton demonstration, we will be sourcing our hydrogen through trailers containing compressed hydrogen. So this is hydrogen operating at 228 bar, and then it gets let down into the medium pressure line at 2 bar, and then dropped down to about 50 millibar for the, or 20 to 50 millibar for the low pressure network. Now, obviously, that's just for the demonstration scale. When we're talking about large scale, so full deployment, there are really two key technologies that will be deployed. There is autothermal reforming, which is effectively combining natural gas with steam to then create high purity hydrogen and high purity carbon dioxide. And then that's combined with carbon capture and storage to then store the carbon dioxide either in a saline aquifer in the North Sea or in a disused gas field. So this is the basis of all of the major hydrogen programs on the books today. They're all using this technology because it is cheap and proven effectively. And you can capture the carbon at around a 97 to 98% rate. So fine, you've got 2-3% that has to be emitted, but that's a pretty good saving from a first bat. And that's looking to take up around 80% of the hydrogen supply. That's a figure that's generally accepted by most parties, apart from, of course, the salesman, because it's effectively low cost. The other 20% is likely to be made up of electrolysis. This is the one that typically gets more kind of public airtime. So you would have probably seen, publications or articles talking about wind going into an electrolyzer and then splitting water. This is the process that we're using at Keele University to provide the hydrogen. This is likely to provide about 20% of the hydrogen at full deployment. It's a good kind of green way of producing hydrogen. The main barrier is just cost. It is just more expensive than doing it the other way. Hence why it will be the minority player when it comes to full deployment. So on to costs and who pays. So everyone's favourite question. If we look at the two different types of production, so the gas reformation, which is termed blue hydrogen, and then the electrolysis, which is termed green hydrogen, they can produce hydrogen wholesale at around £40 a megawatt hour and around £160 a megawatt hour a day. So you can see there that the cost differential is what is driving that ratio of 80 to 20. If we take the majority production, which is the blue hydrogen, that is a carbon abatement, so a kind of carbon cost of around £100 per tonne of carbon dioxide. Now, that's quite an abstract way of sort of representing these numbers, but it's more relevant because that's really what matters. When you're comparing technologies, what matters is how much carbon do you save and how much does it cost, and one over the other tells you how effective it is as a measure. And that's measured through pounds per tonne of carbon abated. And blue hydrogen operates at around £100 a tonne today. Just for reference, that's pretty much on par with offshore wind. So you can see there that the amount of decarbonising that you get through blue hydrogen is on par with offshore wind, which is a good sign, effectively. So on to the trickier question of who pays. At the moment, we don't know. That's the short answer. In spring of 2021, the government has committed to releasing a national hydrogen strategy, and this is expected to set out the regulatory framework that details how costs will be covered and how investment will be incentivised to build both the production and the distribution. And effectively, the additional costs will either fall on energy bills, like with the low carbon electricity support mechanisms, or it will fall on general taxation like the RHI. They're the only two pots ultimately, but we will find out in due course. And clearly, everyone's goal in all of this is try to minimise costs, because ultimately we're all consumers of gas at the end of the day as well. So no one wants their bills to be going up.
Okay. Thank you, Tommy, for running us through the last few questions. I thought everyone was going to maybe make it a bit easy for me and not ask that many questions in the Q&A, but I appear to be wrong. So what we'll do is we've got quite a bit of time left, so I think we'll probably try and aim for a 7 o'clock finish, maybe just after, depending on how many questions we get through. So Tommy, I've been making some notes here of what's come through, and I'll try and answer some myself and then pass them on to you as well. And I think in terms of this process, I think this will be useful for everyone, because obviously clearly there's quite a lot of interest in this subject. So a few early questions that came in. There was a question regarding buoyancy of hydrogen and how will a blend mix? Will it stay mixed? Will it unmix? And I suppose the short answer to that question is that it won't unmix. Once it's blended, it's blended. It was a question that got asked quite frequently during the early stage of the project, and we carried out a desktop exercise through the HSE Science Division, which is the commercial arm of the HSE, where they had where the findings were that it wasn't an issue. And in addition to this, we also used some learning from a gas company in France called Engie, where they carried out some practical examples of this. Tommy, I think you might be closer to the details. You might want to share, what they found.
Yeah, so they effectively found that it doesn't demix, it's almost the first question that everyone asks. We were comfortable that it didn't unmix just through hand calculations, because it's very known physics. It's just different buoyancy of gases, and although they are although the blend is more buoyant, and certainly hydrogen is a lot more buoyant, a bit like releasing a canister of gas in a room, gases have a natural tendency to mix because it's what maximizes the entropy of the system, and so you need quite a strong force to be able to separate gases back out, and you just don't, and just gravity isn't able to provide that level of force to be able to separate the two out. So we calculated that you would need a completely isothermal riser that's at least 100 meters long to be able to get a 0.1 difference between the top and the bottom after a few hundred years. So it's just not a practical consideration that is ever going to impact anyone's appliance. Upon that basis, we were comfortable to not do any experimentation. As Adam says, the kind of sister project, if you like, in France, that's effectively doing what we're doing, but on a French network, has carried out some experimentation to demonstrate it, and it was in line with what you would expect to see.
Yeah. And I suppose, and ultimately that it was approved by the HSE for the first trial, and obviously, sufficient for us to move forward with that blend down at Kill and then beyond within Winlaton. I think, Tommy, there's been quite a few questions around appliances and boilers and things like that. So I think I'll just jump onto a couple of these. So there's a few questions here. So in terms of a blended gas, does it generate the same heat output as natural gas? And the short answer is no. When you add the hydrogen into the gas mix, depending on that blend level, it will reduce the any energy content, not by a great deal. But Tommy, if you can just put the detail behind that, and also just there's questions there around NOx emissions as well in that same space.
Okay, that's fine. So it's a quite a nuanced picture. So it depends which gas characteristic you're concerned about. If you're looking at the CV of a gas, so the calorific value, i.e. how much can I get out of a set volume of gas, then you will have a slight reduction in the maximum heat capacity output. Clearly, you will only see that once the appliance is operating at full capacity, and if you've got a very strong reference gas. But that's not really the important metric, because appliances aren't designed based on gas CV. They're designed based on the WOBI of a gas, which is a more nuanced gas characteristic. And what the WOBI takes into account is both the energy content of the gas, the CV, as well as its flow characteristics through its density. And effectively, it is a measure of how much heat output you would get over a gas valve for a constant pressure drop over the valve. So you can change whatever you want with the gas. You can change its CV to whatever you want. But if you change the density of it as well, then you get the same heat output. And it is interesting that with pure hydrogen, you have a CV that's 1/3 of methane, but you have a density that's 1/9. And effectively, they almost perfectly cancel out. So the amount of heat that you get out of the appliance for the same supply pressure is almost identical. And when it comes to the blend, we are not breaching the current WOBI limits within the gas safety management regulations. So the WOBI limits are 47.2 to 51.4. So that's the range at which natural gas swings around in the system today across the GB system. We're not breaking that range. So in terms of the experience of the appliance and how much heat it will provide, we aren't going to be affecting that. In that you may be affecting the individual appliance if you had a particularly strong gas that then got changed for a blend. But if you look across GB and within all the compliant gases that appliance could see, then there is no change, because the next day it could just as easily see a low wobby natural gas as it could see a blend, and the consumer wouldn't have noticed any difference. In that, I have never noticed a change of gas quality from one day to the next, and that will continue with the blend. And just to pick up on the NOx front, so normally, or the kind of the perceived wisdom is that hydrogen increases NOx emissions. Again, it's a nuanced picture. It does and it doesn't. It depends how your control system works. If you've got a very sophisticated control system that is trying to achieve a certain excess air, so it will pull back the air if it needs to, then you can achieve higher flame temperatures, which could promote more NOx. But that's not how boilers work. As you'll know, boilers work on a fixed air to fuel ratio, and then as the fuel changes, the air or the excess air in the flue will then vary. And so what we see is, because hydrogen requires less oxygen to burn, what you see is effectively a slight increase in the excess air that results as you blend, and that effectively cools the flame by about 5%. It's well within all limits of operability, and what that results in is a slight reduction in NOx. So across fires, ovens, cookers, boilers, you should see a slight reduction in NOx and a slight increase in air or oxygen.
Thanks, Tommy. I think that is a really, really good answer. Obviously, putting me right. In terms of in the performance of appliances. So there's a few other questions around here, specifically around the equipment that gas safe engineers will be using downstream. So from that aspect, as Tommy's said already, there is no change there. So if the current equipment we use, if that's registered as safe to use on natural gas, it will be fine for a blend. There's been questions regarding upstream. So in terms of current gas go seekers within NGN's network, I'm delving away a bit from the downstream, but they'd probably appreciate there might be some NGN employees on here. So in terms of upstream, the current gas go seekers that are in use on the network across all the distribution networks, they're cross sensitive to hydrogen. So essentially, the cross sensitivity relates to the CO alarms that are currently in all the gas detectors, and what happens is that there will be the CO alarm would go off if you were using that on a blended network. So in terms of managing the trial, we've got specific equipment that's being utilised for that in Winlaton, and for rollout, there's already significant engagement with equipment suppliers on producing a piece of equipment that will be ready for blended hydrogen. So at the moment, for the process managing for the trial, we have separate pieces of equipment, but looking further afield, there'll be equipment available that will be able to detect a blend without giving you that cross sensitivity. Tommy, I'm not sure if you wanted to touch on anything extra on that.
No, it's just to say that that's the reason why we're using different survey equipment. We have carried out experimentation to see if that affects the fixed CO alarms in homes, and what we found is that for the permissible leaks that one would allow for, you shouldn't see any false alarms. So just to add a bit more.
There's some questions been asked around the different applications of natural gas in respect to the different industrial processes and commercial installations. So I think from a commercial perspective, there's quite a lot of commercial applications at Kill. So we're confident as a project that is mostly covered off. The other area that we're working on, and again, I'll hand back to Tommy, is the industrial applications of using 20% hydrogen. So Tommy, if you could maybe share a bit of work that Progressive Energy are working on that area.
Yeah, so we haven't touched upon industrial usage much to date. The reason is because our trials haven't required us to do so, but we absolutely recognise that out in the big wide world, we're going to have to understand how a blend could impact industrial users. So we are working with another programme that's funded for the government to run industrial trials, where we're looking to start actually in about a week and a half's time a very similar experimental programme that we've run for domestic boilers, but with forced draft furnaces, where we'll then be demonstrating the operability of boilers using a 7 megawatt steam boiler at the Unilever site, and then also covering Blastworks up at Pilkington with their 55 megawatt furnace. Now, we're also working out other work packages as well, looking at ceramics, gas turbines, gas engines, baking, etc. So the idea is to try to cover off all of the uses of gas, both in kind of generic heating appliances as well as direct fire, more specialist processes like kilns. And the idea is that combined with power should cover off the vast majority of the industrial users. Clearly, CNG is another area that needs to be looked into, but we're hoping to cover off that as well. So the idea is that within the limits of the budget that we have, we will try and cover as many of the industrial users as possible to try and build up the evidence base to demonstrate that it is safe to operate their equipment with a 20% blend.
Okay, thanks, Tommy.
Sorry, I just want to pick up, I've seen in the comments talking about lambda control. That's a good point. We've tested boilers with lambda control, and no, you don't see a increase in NOx. There's enough air floating around that you don't see any meaningful increase in the NOx emissions. So yeah, just to cover that off from the responses to the bit around NOx earlier.
Okay, no, that's good point, Tommy. There's quite a few of them. That was the ones I managed to catch up earlier. I think there's a question that's been asked quite a few times. The slide deck will be sent out along with a link. I haven't asked Vince to do this yet, who's looking after that, but I'm sure we can send the slide deck out and definitely the link. There's a question here around moving from 20% to 100%. You know, would you go through 30, 40, then 50? And the answer is no. It would be 20% and then 100% hydrogen. The main reason for that is that all of the testing that the project team have carried out to date is that when you start getting beyond 20%, 25, 30, do start seeing the performance of the appliance affected. So a 20% blend was it's a scientific decision, but also there is the additional factor of when the existing gas that's in with the next work and the commercial billing regime that we have in place to date. So it's how that all fits together. And when I talk about the commercial billing regime, if we start adding more hydrogen, and we obviously start to reduce the gas quality further, and it has a whole change with the interlinkness of billing. I'm clearly going to go down a rabbit hole there, but essentially it will be 20% or 100% hydrogen. Tommy, I'm not sure if you've seen any that you might want to pick up on.
Yeah, there's a couple that I just want to that are reoccurring a couple of times. It's worth just picking up on. So first of all, tightness testing. There's a lot of questions on UP1 and permissible leaks. So the basis of UP1 is to try and pick up, as you know, small or non-permissible leaks. There is quite a lot of research out there that has shown that a permissible leak is effectively a laminar leak. There are two flow regimes of a gas. You either have a laminar flow or a turbulent flow. If you're in the laminar flow regime, you are dominated by the viscosity of the gas. If you're in turbulent, then you're dominated by the density of the gas. In all tightness testing, the permissible leaks are all governed by viscosity. They're all laminar leaks. And the change in viscosity of the blend relative to natural gas is completely negligible. It is less than 1%. So, i.e., for the same pressure within the pipe, for the same leak path, you're going to have no extra gas coming through. And so what that means is that the tightness test criteria remains the same. Even though the molecule is slightly smaller, it's about 15% smaller in terms of its diameter, that really has no impact whatsoever. It's the difference between throwing a grape relative to throwing a pea through a tunnel. Kind of any leak path is just so many orders of magnitude greater than the diameter of the molecules, that having a slightly smaller one really has no impact whatsoever. And if we had discovered that was the case, and you could separate out hydrogen that easily, we would be making a lot of money in the gas processing industries, because it would be a fairly lucrative business. So that's tightness testing. I hope that's clear. In terms of water vapor, there's no increase in water vapor. This is again a kind of classic. It's kind of almost paradoxical. So if you think about what we're doing, we're swapping methane with hydrogen, and the water vapor that's produced from combustion is based on the hydrogen content of the fuel, and we're swapping CH4 for H2, so actually reducing the amount of hydrogen within the fuel. So it's slightly paradoxical, but we are directionally slightly reducing the amount of water vapor that would be produced, but it is well within the range that you would expect to see across the gas band that's allowable within the UK. You're talking sub 1% changes in the water content, so you really aren't going to see any difference. And in terms of its corrosive effects, most of the corrosion that's caused is due to any carbon dioxide that is dissolved in the condensate, as well as any nitrogen-containing species within the natural gas from effectively the gas wells. So because the hydrogen is coming out from a production unit, it is a much higher purity gas relative to the stuff that comes out of wells. So there should be far fewer impurities within it, which means that you should have fewer nitride components, and therefore your condensate won't be as acidic. It will still be acidic, but it won't be as acidic. So it should be directionally slightly better for pipe work. I think that was all the main ones, but if there are other ones that people have,
Tommy,
please put them in.
Yeah, so there's quite a few that's come through. I think just before I put this one here, remember most the work that we've done to date is all for the HyDeploy project team is on a 20% blend. So 100% hydrogen relevance to some of the questions might not be as applicable. So when Tommy's answering, this is all really focused on 20% blend, unless he states otherwise with regards to 100% hydrogen. Yep. Of course, we'll answer them as well as best we can, but there are different projects that are undertaking that, and you can find that information in the public domain at the moment. So, Tommy, there's a recurring one around the upper explosive limit and the lower explosive limit for a blend. Just wanted you to talk through the process that what we've mentioned gas characteristics earlier on, and suppose talk through that briefly, that process that we've undertaken, and what we concluded.
Yep. So probably one that's more relevant is the LEL, because obviously that's the start of the Campbell range. So there's actually quite a lot of debate around what the LEL is of natural gas. You either take it as 4.4 or 5. based on what standards you look at, but actually actual gas quality data looking across the typical gas supplies in the UK puts it between about 4 and 4.5, but that doesn't really make any practical difference when it comes to the detectors or the procedures. In terms of pure hydrogen, that has a LEL of 4%. When we're talking about a 20% blend, which obviously the topic of this discussion, then the LEL shifts from 5 volume percent to 4.9 volume percent. So you do get a very marginal reduction in the LEL, but it is well within what you would expect to see in the kind of distribution of gases within the UK. And based on what detector you use, you could very easily have one that's set up for 4.4 based on what standard the manufacturer complies to. So yes, there is a very slight reduction, but it's well within the bands of normality, both for real world gas and what the what the detectors are set up to take. When we look at the upper end, you do see a slight increase. So pure hydrogen has got a UEL of 74%, obviously quite high. Natural gas is typically taken at 15, but again, there is some debate over whether that is really 15, but that's what we take. And the 20% blend is 18%. So you do have a slightly broader flammable range when it comes to a blend, but that's just a function of the gas. I think that's probably covered off the LEL questions. There are a few questions on the smell of the gas and whether we'd still smell it. But the answer is yes. The level of dilution that you would expect to see with a 20% blend is within the error limits of a nose. So your nose works on the same basis as your ears. It works on a logarithmic scale. It's why you can smell very faint things and you can smell very strong things, and why you can hear a whisper and then be able to stand next to a jet engine. Most of your senses work on logarithmic scales. So when you slightly reduce them by a small factor, your kind of sensing mechanics really can't tell the difference between it because it's looking for jumps of factors of 10 before it can really differentiate between them. And that's been quantitatively demonstrated through hand calculations and has been physically confirmed at Kiel, where we had rhinologists, who were the kind of smell people from the GDNs, go and test the gases when they didn't know whether there was a blend or not, and all the blend levels, they can't tell the difference between that and any normal gas, and all of the chronology passed on all the blend levels. So it confirmed what we knew was true. When it comes to pure hydrogen, which obviously a different world, one of the stipulations that the HC will have is that the smell of gas remains. So anodorant will be put in exactly how it is with natural gas, so the smell will be the same. So there should be no kind of recalibration of consumers' noses or gas safe engineers' noses to get into a hydrogen world.
Okay, thank you, Tommy. I think I'm just going to rattle through a few quick ones now. In terms of there's questions around hydrogen production. So I think I think Tommy's touched on them already. But in terms of the trial at Kiel, that was produced in hydrogen was produced using electrolysis and electrolyzer, and as Tommy's mentioned already, we'll be using trailered hydrogen, which will be carbon neutral. As we carbon neutral production, or sorry, not production. It will be carbon neutral by the time it's delivered to customers. There's been questions around when we get back to some normality, we'll be able to welcome visitors to the plant. That's certainly the case. We have, I think, Tommy, correct me if I'm wrong, we did have something planned for gas safe earlier on in the year, but due to C-19, it was curtailed.
Yeah, so we were going to try and set up a visit for gas safe engineers, but then COVID hit. Yeah.
So we'll look to, when we can, we'll look to hopefully reinvigorate that process, but we'll have to see where we are. And I think one that did keep coming through, we have touched on it, but in terms of existing appliances, they won't be able to burn on 100% hydrogen. We would need to replace them with a new 100% a new boiler or new appliances. There was a question there relating to does this mean that if we go to 100% hydrogen future, does it mean that there will be less reliance on ground source heat pumps, or in the counterfactual of electrifying heat? And the gas networks have always been quite clear that for a carbon neutral future, we're going to need a mix of both. So we're going to need these electrical installations for electrifying heat, and we're going to need hydrogen to get us to this carbon neutral future. It's something that we're quite clear on in that aspect. Tommy, as I've been talking there, have you seen any other questions you feel the need to answer, or if there's been enough interest?
A couple. So one person has asked around flue gas analysis in terms of the CO and CO2. So with less carbon in, you get less carbon out. So both reduce CO and CO2, but by some magic, they reduce at approximately the same levels. So we suspect this is actually a large reason why CO and CO2, or why the CO2 ratio was actually selected as the measure of combustion, because what we found is that flue gas analysis maps almost perfectly with the Wobbe number of the fuel, i.e. lower Wobbe number, lower carbon dioxide and lower carbon monoxide. This is actually the basis behind why we use Wobbe and the limits that we have, which was some research carried out by Dutton in British Gas in the 80s, and sorry, the 70s, and the blend conforms to those principles. So although you see a reduction in the CO and CO2 when you do a ratio, you get effectively the same number that you would expect to see with a natural gas that has the same Wobbe. So you don't have to adjust any of those criteria, because the criteria naturally accounts for the Wobbe of the gas. It's quite a sort of elegant system, really. So yeah, no change there. And there was some other questions I was going to pick up, but I've lost them now.
No, it's only the same.
Yeah. So there's a couple on ventilation requirements, but for so I suppose there are two types of ventilation. There's pre-combustion, post-combustion. When it comes to pre-combustion, so trying to mitigate the risk of flammable environments. Leak dynamics is very interesting. So what happens when gases leak is that they come out of a source and they will start to accumulate high up. So they could accumulate, say, under within a cupboard, or they could accumulate up on the ceiling, and then they will slowly start to come down the room and then increase the concentration within that cloud. And if it reaches a flammable cloud and then reaches, say, a switch or a light bulb, then it will go. But what happens is that gas doesn't just, it won't just fill the room sort of permanently over time. It will start to escape through gaps and holes and through the ceiling, etc. And what happens is you reach a stable state where the amount of leak that's coming into the room is the same amount of gas that's coming out of the room, and you've got a stable environment. And if that environment is flammable, then you've got a risk, and if it isn't, then you've got a gas that needs to be gotten rid of and then capped off. With a blend, what happens is, although you could have a slightly greater leak rate if you've got a large leak, which is a turbulent leak, which is what I was trying to get at earlier. So you could have a slightly larger leak with, like a full bore rupture, for example, where you've got more gas coming out. Because it's a more buoyant gas, it drives ventilation harder than natural gas. So it's basically self-correcting. So although you could get a greater, higher leak rate, it will force a higher ventilation rate through the room, which means that you don't get an increase in the concentration of gas within the room, which means that from a ventilation perspective, all of the current areas required map across to a blend. And then when it comes to post-combustion, ventilation is really there to get rid of toxic products, i.e. CO. And because a blend of gas produces substantially less carbon monoxide compared to natural gas, all of the ventilation requirements are perfectly adequate. You're actually producing less carbon monoxide in the first place. So trying to dilute it with air is actually an easier job with the natural gas ventilation specifications.
Okay, Tommy. I think I'm going to draw it to a close there. I think we've done our best in answering the questions. I think I just want to thank everyone for joining us this evening, and hope that you have found the webinar useful and interesting. We would ask that there is a feedback form that will be sent out to yourselves, and it's just been added to the Q&A. So if there are any other burning questions that you feel we haven't answered, then please put that there, and we'll get a chance to see them, and we'll try and answer them. But if you can please fill out that feedback form, it'd be great for us to try and help us understand how we can shape these further engagements with yourselves, and make it more interesting and more relevant if need be. But in the meantime, if you keep an eye out from a gas safe bulletin that will be issued in the near future, and from Tommy and myself, thank you very much for joining us, and hope you have a good evening.